Thanks so much for being here and hanging around till the bitter end. My husband's here, and I said, you really need, he came to San Diego, why not? You really need to be here because there will probably only be 6 people in the audience, and so we need to fill the ranks. So thanks for being here. It is just an incredible honor to have an award bestowed in my name before I'm dead. And I did hear the rumors about my being dead. It was a little surreal, but I'm over it. It is also an incredible honor to be able to be present when Eltraport wins the award for the first time because he is astounding, and I couldn't be happier about that. But it's just so special that the organizers and the technical committee would indulge me to share with you my reflections on software architecture. We all know as architects that the decisions we make are influenced by the systems we've worked on, the technology we've used, the companies we've been with, the company we keep. And just so, my experiences in software architecture in the places I've worked, IBM, Eastman Kodak, and academia for a while, at the SEI for several decades, working with scores of different customers and researchers over lots of different countries and lots of different domains, has given me a window on the software development field. And it's from that window that my little perspective on software architecture comes. And I would like to share with you a little bit about the history of software architecture, and I will try to be as factual about that as possible. And then when I get to what I see are some of the current challenges, and what I've seen here are some of the practices and some of the research and some of what I see needs to be done, those will be my opinions. So let me start out by saying, that was very important. Let me start out by saying that I believe that the quality and longevity of any software reliant system, of which there are very few which are not software reliant, depends on the software architecture. Now, Grady Booch, in his opening keynote, said that an enduring architecture is an intentional architecture. I believe that. But I would go further to say that a system that is successful, it is fit for its purpose, however long-lived it is, because sometimes the purpose of a system is not to live forever, depends on architectural decisions. When we see bottlenecks during various loads, we know we've made some bad architectural choices. When we are trying to do continuous deployment and we can't follow the release plan because there's too much coordination between teams, we've got some architectural problems. When we have difficulties in test, we can't integrate and test properly, then we know we have some architectural issues. So the architecture is supremely important. I know that from my experience. I think you probably know it as well. And why is the architecture so important? Because it's that abstraction that allows us to reason about the behavior of the system, to analyze the system, to communicate with stakeholders, to guide prototypes, and so on. So architecture as a concept has been around since the 80s. And it's always been about boxes and lines, structure, and we haven't always agreed on the definitions, but it's about important decisions. So on the SEI website, if you haven't visited it, there are about 150 different definitions of software architecture that people have contributed. Martin Fowler says it's the hard stuff. You heard Grady Booch say it's the important design decisions that have significant economic impact. The SEI says it's the set of structures needed to reason about the elements, the relations among them, and the properties of both. Well, what about elements? Well, elements have responsibility, elements have boundaries, elements have interfaces, the connectors or those relations are first class, whether it's data flow or control flow. And what we know is that by reasoning about the behavior of the system, we have a way of analyzing, we have a way of making trade-offs. So what kind of trade-offs are we making? If you believe in the gospel according to the SEI, then you know about quality attributes and you know about the importance of quality attributes and how quality attributes are not made up for the sake of saying my system is going to be interoperable or open or secure or modifiable, but they're driven from business goals. They're driven from the drivers that we need for this system to behave as it should under the context that we see and under context that we might not be able to see. And so the whole set of quality attributes is a primary driver. Now, this is the famous eyeball architecture chart from the SEI. You probably have seen it. You don't get the eyeball part yet if you haven't seen it. But the whole idea is that we have these business goals, these business drivers, and it could be that we want to have the market share, we want to be able to grow the market share, we therefore need a scalable system, so we have to think about scalability, but we want to build this system. And maybe one of our business goals is a technical goal. Maybe we want to use some sort of a technology stack because other people in our domain do and we have to interface with them, or maybe we want to jump on the bandwagon of continuous deployment, and this is our goal. And so we build this system, and it's code, and the code is the reality. But how do we know? Well, we certainly don't want to test it out without any sort of preconceived idea of what's going to happen. And so we have the architecture. And the architecture allows us to understand what we might be getting by way of the system. So if, in fact, we want a system that has a specific response time, we want it to be very responsive to our customers, well, then we have to look at throughput. And what do we look at in the architecture? We look at the frequency of the element communications. We might look at the data volume. We might look at the thread overhead, the thread allocation, thread mobility, and so on. Now, if you notice from this eyeball chart, and now you see the eyeballs, it's highly iterative. It was never meant to be the thought that you divined the architecture from it, you build the system. You do this little evaluation once in time, you build the system, and life goes on happily. We know that's not life, and so we continuously iterate on all of these activities. Okay. The 1990s was billed as the golden age of software architecture. So if I'm going to take you through the history, I need to get you in the mood. Where were we in the 1990s? Now, I chose 1996 as being sort of representative of the 90s. And in 1996, if you're from the UK, in particular if you're from Scotland, they cloned a sheep named Dolly. And this was hugely controversial because people were very frightened that there would be human clones. But alas, in 2003, Dolly was euthanized, and I never got my clone. I don't know about you. Zika virus now on everybody's radar. What was happening in 1996? The mad cow disease. And so that's what started this concern when you're crossing borders through countries. Have you been on a farm? Have you been around livestock? Because everyone was concerned about the spread of mad cow disease. Now, Clinton was president. Actually, he was president from 92 to 99. Some things don't change. Jerry Maguire was the most popular movie. And if you don't know Jerry Maguire, the tagline from Jerry Maguire was, "Show me the money." And Show me the money seemed to be really a good mantra for the 90s. That was when all the dot-coms were founded. Eventually, many of them didn't show any money, but that was the goal. Now, if we look at the technology side, you see those things on the right are not walkie-talkies. Those were cell phones. Cell phones were like bricks. And they were available in few countries, and they were very expensive. What else was going on? Well, right now we have this one device. That's a phone, that's a camera, that's a personal assistant, as well as many other things, the GPS and so on. But digital cameras came out during this period, and they were digital. They were also very expensive. Palm Pilot came out in 1995, and for those of you who don't know, Palm Pilot was the first personal device assistant, PDA. Okay. Amazon was founded in 1995, and nobody thought they had a business model. How were they ever going to make a business? Google came out in 1996, and aside from the small crowd at Stanford, nobody else knew about them. So this was the technology of the times. Oh, we were using Microsoft 1995, and Office 1997 came out on CDs, but you also had the option of getting it on floppy disks. There was a big debate, as you can see on the Time cover. Who was going to control the internet? Would it be Bill Gates and Microsoft or Netscape? Who? So that's where we were. Now, what was happening in the software development world? Well, for me, it was kind of interesting because I lived this. Object-oriented technology was taking off in the 90s. And so, in fact, the 1990 cover of Communications of the ACM depicted Lego pieces. And the whole idea was with objects, everything would fit together like Lego pieces. Alas. Sounds familiar. We have similar things right now we're selling. Microservices? Anyhow, this was a whole new way of thinking about systems, a new way of not only programming, but designing systems. And with it came a whole new culture. Now, I was very much involved in that culture, whose meeting was OOPSLA. This was a conference attended by maybe 2,500 people in its heyday, and this is where all the object people hung out. Grady Booch was one of those people. Kent Beck was one of those people. Dick Gabriel was one of those people. I had a lot of fun object friends. On the side of managing software development, the overriding paradigm was the engineering paradigm. And at the SEI, the capability maturity model for software was the Bible for how people would manage their software through well-defined processes across a gamut of process areas. So I joined the SEI in 1990, and my friend said, "Why? Why are you joining the process place?" And I said, "Well, I think they do other things than process. I think we're evidence they do other things than process." But I grew great appreciation for the engineering approach and all the processes and what had been put in place, because the discipline was in an era that kind of boost and guidance and maturity was really needed. But just keep that in the back of your mind. We have these two parallel things going on. In the software development world, it was object technology where things were going. And in the management side, it was more of an engineering paradigm. Okay, now, why was the 90s called the golden age of software development? Well, Parnas did his work in the 70s, started anyhow, talked about information hiding and program families and structure, so certainly some foundations were laid down then. In 1975, Fred Brooks wrote the Mythical Man book, Mythical Man Month book, which is really a compendium of his essays, and one of which is The Single Architect, and so some thoughts were there. But it was really in the 90s where these seminal pieces actually were published. Perry and Wolf had a paper about structure, and this was really some of the earliest thoughts about software architecture and structure. But one of the things that was needed was a vocabulary. How do we talk about these structures? What do we call them? How can we communicate with one another? And so the Gang of Four, John Vlasides and others, Eric Gamma and Ralph Johnson, and you know them, were working, they were in the object community, on the Book of Design Patterns. And the design patterns, as you all know, give us formality around a set of problem-solution pairs. In the design world, they have names. We all know bridge and adapter and all of the rest. That came out in 1995. At about the same time, Mary Shaw and David Garland were going through a similar exercise at the architecture level. And they published their book, which put forth the whole idea of architectural styles. It was actually a fundamental schema for structure, talking about the kinds of element types and responsibilities and rules. And from that, we learned about the name pipe filter, and we learned about blackboard, and we began to have a lexicon that we could use to discuss architecture and architecture chunks. Bushman came out with his pattern-oriented software architecture, and others followed. Now let me take the bottom path, because this was also really important. In 1994, Rick Kaseman, who is back here, and some of his pals at the SEI, presented a paper that was published as part of ICSE 1994 in Sorrento. And it was on software architecture analysis method, which was a scenario-based approach for analyzing the modifiability of a system through its architecture. Now, from that idea of a scenario-based approach, we at the SEI said, wow, I wonder who else is doing architecture evaluation. We had architecture evaluation workshops. We found out that there were an assortment of questioning techniques, and questioning techniques involve these scenario-based approaches. They involve checklists. Joe Maranzano at AT&T took a checklist approach. Involved surveys. People at Siemens did surveys. And then there were measuring techniques, and that was a paltry few. Nortel did something by way of measuring, actual metrics for software architecture. I would say there are still very few offerings in that camp. But out of the scenario-based approach then came the ATAM and many other variations of architecture evaluation. So really important to think about. We know structures. We now have a lexicon. It's important to evaluate them. Well, how do we depict them in order to evaluate them? You heard Grady Booch talk about Philippe Cruchten's 4+1 views, and that paper came out in 1995, and that gave us the 4 views: the physical, the process, the logical, the development views, as well as use cases that talked about the behavior of the system. And that spawned a whole lot of innovation around looking at architectural views and viewpoints. Rod Nord, who is here someplace, and his colleagues at Siemens wrote a book on viewpoints, and Owen Woods, who was here earlier, wrote a book on viewpoints. The SEI had a book on views, and this gave us a way to talk about the views of the architectural structures. At the same time, people were thinking, well, we should do this in a formal way, because only if we do it in a formal way can we reason mathematically about it. And so people, David Shaw, Mary Garland, and others, Rockwell Collins, developed architecture description languages, Write, Acme, Meta-H. And then UML. Now, Grady mentioned UML. Where did UML come from? Was it originally for describing architectures? No. Actually, UML was about some sort of unified approach to describing object-oriented design, because Grady Booch had his cloud approach for describing. It's a little fluffy. Jim Rumbaugh, who was also big in the object-oriented community, had a different approach, a different symbology for representing classes, and he actually had some performance diagrams. And then Ivar Jakobsen was the use case guy. Okay, so they got together and they formed the Unified Modeling Language, or UML. When UML came out, and it was released 94 to 95, and I think the big splash was in 1996, my thinking was, the good news is we have UML. The bad news is we have UML. Why? Because as an architecture, representation symbology, it was really lacking. It didn't allow for the kinds of depictions that I wanted to reason about in a software architecture. It has improved. Okay, we move on. The SEI did a few things too. We created methods, we created tools, we created techniques. I should say that the architecture project that I led was started in 1994. There were some architectural efforts before that at the SEI. They got fused together as a project in 1994. 1996, it got glorified as what the SEI called an initiative, which means it got money. And from that, many of the things that have been referenced at this conference actually were created. And what's particular about our view of what we call architecture-centric engineering is this quality attribute focus that I've mentioned, the quality attributes being derived from the business goals so that architectural decisions are actually tied to business goals, that all of the methods involved the system stakeholders. And we're talking about the whole gamut of stakeholders, the testers, the developers, the users, the business managers, the sponsors, and so on. And that they be grounded in state-of-the-art techniques. So we're not talking about just using the name modifiability, but understanding what are the formal techniques underneath that name that allow us to actually reason about the behavior of the system. Now, over the years, thinking progressed, and there were lots of innovations, patterns and then tactics to implement those patterns, component-based approaches with rich interfaces that were imbued with some of the quality attributes, company-specific product lines, families of software systems that actually shared a common managed set of features and were allowed to vary in specific ways. Model-based approaches, of course, architecture models generating code, aspect-oriented approaches, frameworks and platforms from which ecosystems emerged where the connectors or the protocols became supremely important. Standard interfaces, things like Corba were for distributed systems. Standards, 1471 for architecture representation. We began to have standards for documentation, for evaluation, and other facets of architecture, and service-oriented architectures to support a more dynamic modularization. Now, one of the things that I see throughout all of these are some persisting themes. We're trying to think about how to decompose in a way to be more modular, whether it is at development time or runtime. And there's this tension between what is common that we can reuse, whether it's services, whether it's a platform, whether it's code, modules, I don't care what it is, and how it can be varied, tailored for a particular situation. There's great tension there. Reuse as a topic was introduced at the first software engineering conference at Garmisch. This idea of a component factory actually was suggested back in the 60s. But we never really got the fact that reuse was not for reuse. Reuse was for economics. It was for saving money. And you only save money if what you reuse has economic value, and how you are allowed to vary things can be done in a prudent way that's economically useful. Okay. Then there were a whole bunch of conferences that sprung up. WICSA came up in 1999, other research conferences, practitioner conferences, and SATURN, as you heard, was started as something that would be focused on practitioners, but would bring some of the research to bear. So it would be sort of in the middle. There are also lots of tracks at other conferences, tracks that were devoted to software architecture. In my humble opinion, I still think there's too big of a gulf between research and what goes on at the practitioner conferences. I spoke at QCon in London, and this is a developer conference, and I then go to ICSI and I think, wow, these people are worlds apart, but we're all in the same field, and we're all trying to make the world of software better. There were some related shifts. So in the 90s, I think people have always done some sort of incremental development because it just makes sense. But in the 90s, lightweight incremental development methods appeared. There was Scrum, crystal clear, extreme programming, and it culminated in 2001 with the Agile Manifesto. And this was interesting because I talked to you about, the object community and the UPSLA community. It was those people who rallied together and were agilistas and got together at Hillside and decided that they were going to proclaim the manifesto. And this is, we will embrace change, and we will have frequent releases, and we will test early, and we will do things incrementally, and we will eschew all big documents. The word process became a nasty word. And big front architecture documents, you ain't going to need it, and so we don't want it. Now, the pity there is when this gets translated to the masses, it says to the masses, we don't need architecture. What was really said is we don't need an architecture document, okay? But we don't need architecture. And Grady kind of talked about this. Not to name drop, but I'm friends with Kent Beck too. And sat down with him a long number of beers discussing, come on now, you can't be serious. And it was, as Grady said, because Kent's just really smart, has lots of experience. But it was also because all of the systems that he was developing were in the same domain. And the mental model, the virtual framework existed, and they developed under that. And under that, you could code and refactor and come up with something because you knew what the basic structural decisions that needed to be made for that domain were. That just wasn't true for a lot of the rest of the world who bought this, completely drank the whole thing, and said, we do not need to think about architecture because through refactoring we're going to get an architecture. Now you get one. We also had the whole open source movement, and the open source movement was terrific, but not so terrific until we had mechanisms in which we could share and frameworks in which we could plug in, and Eclipse and others were developed. Okay, so what changed? What changed was, with the beginning of the internet, and for the last 20 years, everything has become increasingly connected. And with this increased connectivity, there's an increase in scale and complexity. We have everything, it can't be hierarchical anymore. It has to be decentralized and distributed. There's tsunamis of data. It's this increased operational tempo. We live in this instant gratification world where everything has to be fast. And we're used to this. We don't have to remember what anybody's name is. We Google it, and we find out. So we don't even tax our brains anymore. We can get information quickly. We want systems quickly. But there are all sorts of now interreliant ecosystems that challenge us. Autonomy. We're using autonomy to enable scale and to enable quick decisions. Everything's connected, and that makes us infinitely more vulnerable. So there are vulnerability issues. And we have this whole possibility of collective action. Through social media, through autonomous agents, we can unite in ways we never could before, across the globe, marshaling people in countries and organizations to overthrow leaders, to do good things. In fact, we're in a world where people, computational units, autonomous agents are peers in this system context that we live. And there's a whole gamut of disruptive and emerging technologies that we're all aware of. And my little mouse stopped working. Okay. From cloud to social media to smart everything in the universe. Oh, okay, I heard one yesterday on the news. Have you heard of smart contact lenses? It's the newest thing, yes. Smart contact lenses, where I'm looking at EPEC and I'm taking her picture and she doesn't even know it. I mean, that beats Google Glass. Smart contact lenses. But think about it. You're here with this theme of the Internet of Things. This is a seductive set of technologies. And, right. And against that, a whole new set of software development trends. So we have new application frameworks. We have Ruby on Rails. We have distributed development environments. We have all kinds of cloud strategies. We have new databases, NoSQL, NewSQL, because we have big data. We're using machine learning. There's a complete awakening, reawakening of artificial intelligence and all of that expertise because now there's a purpose. And we have a gamut of static analysis tools. I could spend time talking about that, but I won't. We have dashboards. Dashboards to monitor the processes you're using. Dashboards to monitor our system when it's running. Dashboards to monitor social media to understand how our systems are doing in the eyes of the rest of the world. We have DevOps. We have containers. We have microservices. Well, what does all of that have to do with software architecture? And what are the real challenges here? So, to me, I'd like to ratchet it up and look at the top-level challenges that I see. Number one is this whole idea of accelerated capability. Everything is about speed. Everything is about release time. Everything is about continuous release. And even if you have a deliberate system where it's not going to be continuous release, you want it faster. You want short cycle times. It's about the rhythm. It's about velocity. Scale. Scale in terms of not just numbers of lines of code, number of things connected, number of different kinds of things connected, number of different processes firing, number of different physical entities hooked up together, amount of data being generated, and we have what I'll call assurance. Now, I'm not just talking about security, and we all know security is a big topic on everyone's mind, but I'm talking about assurance that the system behaves as it's supposed to, that it costs as much as it should, that it's delivered when it should be, that it has the right responsiveness, the right real-time performance, if it's a safety-critical system, the right availability and security, and more importantly, that we have evidence for all of the above. Now, someone said that data is not the plural of anecdote, and certainly evidence is not the plural of anecdote. We need to have data, whether they are proofs, whether there's empirical data, we need simulations, we need to be able to quantify, substantiate, provide evidence for what we're delivering. It's time. Where's architecture in all this? Well, if architecture is the abstraction that allows us to reason about trade-offs, when you're in that intersection of something that has to be delivered fast, that is of great scale, that you need to have some assurance about, you're making trade-offs. And how can you reason about those trade-offs. So let me just take a brief tour through some of these challenges, and I'll couch some of the things that I heard here and at other SATURNs and I see going on in terms of these challenges. Accelerated capability. I think people have always been using incremental approaches. And this whole idea of the backlash of using agile, and I hate it when people say I'm doing agile. What are you really doing when you're doing agile? But you can't have architecture. Jim Highsmith gave a wonderful keynote at SATURN 2010, and if you weren't there, look it up, when he actually talked about how that just doesn't make sense, that what you really are after is agility, and agility means agility in structure as well as agility in how you deliver the system, and that's what gives you value. And in fact, you will not have that agility and structure unless you focus on the architecture. So you've heard lots of people here talk about how, in fact, you can take an incremental or agile approach and use sound architecture practices along the route. Elcha gave a wonderful talk this morning about architecture road mapping as part of that. We have case studies on our website, but the idea is you want to have the gross scheme for decomposition, and you want to be able to decide on those cross-cutting strategies that deliver on the most important quality attributes that allow a scaffolding under which people can do incremental development and continuous release. Because unless you put some of that in place, the rest of this is not going to happen as planned. So in the process, though, it's very likely that you will make some shortcuts. You will make some technical decisions that set up a technical context that is actually going to be expedient at the time, not incur a cost of delay, but over time affect this cost in release, increased cost in release, increased cost in change, you're accumulating debt. So the metaphor that Ward Cunningham used in 1992 as a way of explaining the need to refactor to his product manager is something that people have now focused on. This is very important. As you accumulate debt, you get to the point where you no longer please your customers. You can't enjoy the release plan as scheduled, at least at the cost that you want. And we are living technical debt, but we don't understand everything about it. And so there's research gathering as close as 2 weeks ago. And what are we researching? Well, how do we manage technical debt? How do we detect technical debt? So we need to think about a timeline for when the debt occurred. How do we detect it? We use bug and issue trackers. We use static analysis tools. We use architecture analysis. And it's really context dependent. So I can't give you the tool that's going to say, aha, here's your debt. Can be domain specific, can be even within a domain specific. But in order to manage it, you have to put it on a timeline. What we found, and I think this was referred to at some point during the conference, the SEI did a study. Other people have echoed this same finding that bad architectural choices are at the top of the technical debt heap, and in fact the most costly to repair. So this was again a little diagram that Elcha showed this morning, but for those of you who weren't at Elcha's talk, you know, as you are looking at your backlog, there are things that you will do that are visible and have positive value, and those are the new features. There are things that are invisible that would have positive value, but how to estimate the cost is kind of a lumpy process. And maybe you're going to move to a microservices architecture. That's tough to estimate how much that actual movement is going to cost, but maybe you will get great gains in deployability. Maybe you have to make some infrastructure changes. Maybe you like to bring in some new DevOps tools. On the negative side, well, very visible are defects. And so you want to fix those because those are giving you persistent and real pain. But then there's the technical debt. And most developers know they have technical debt, but the people who are making the feature roadmaps and those people who are controlling the destination of the product family and the releases don't always appreciate the technical debt, and it is often very difficult to quantify and communicate. I think still a challenge for all of us. Would you agree, colleague? All right. Okay, so people have moved beyond Agile because you can use Agile development techniques, but you can get a Scrum fall. And the fall is that you don't carry out any sort of commensurate technique from the development operations seam. And so now we have continuous release, continuous integration. We have the build, deploy, test, and release cycle. And everybody is focused on the culture, how you team, the practices that you use, a lot of lean thinking, and the tooling. It's automation, it's static analysis tools, it's performance dashboards. You are trying to automate the whole process. And in fact, if you're going to really deliver on these very aggressive release plans, you really have to automate. Now, Owen Woods gave a wonderful talk at this SATURN where he talked about there's something beyond DevOps, and that's production. And this doesn't take us far enough. And there are also concerns about production and being able to stretch this to production. We can't stop at ops. We have to go to the production side where there are some real concerns. And so, to me, that was a very enlightening talk. If you weren't there, look it up, because it shows us that this trajectory of being continuously flexible and being able to deliver continuous value has to go all the way through to production. Okay, where's architecture in all this? In fact, to many developers in a continuous release environment, the architecture becomes a commodity. It's somehow disguised in the build scripts. And so, was it important anymore? Well, in reality, if you don't make the right architectural decisions, you can be blindsided. Because if, in fact, you don't decompose for continuous deployment, continuous release, you're going to have a stalemate. You might have too much communication needed between teams, and that is going to bog you down. So you need to think about deployability. That's an architectural concern. You need to think about modifiability. You need to think about testability, because part of this build, deploy, test, release cycle is testing. And if the architecture does not lend itself to this facile, quick testing, you are going to have difficulties. Now, a lot of people are thinking, okay, the way that I'm going to decompose my system that makes it ideal for a DevOps culture is, of course, microservices. And everybody is moving to microservices. And microservices are, as we all know, a service is a deployable unit, and it can be a single service or a tight cluster of services. And then there are lots of other things that go with it. Paul Mearson gave a wonderful talk here at SATURN where he said, there's some hype here. There are lots of benefits, but there are lots of pitfalls. There are a lot of challenges. You know, it is not the silver bullet. And so when you're thinking about microservices, where's the architecture? Well, you've got to think about how you're decomposing into microservices, and you've got to think about the communication across those microservices. And you need to think about their relationships. And so, yes, you will get the dynamic discovery and the dynamicity and the scalability, but be careful about the deployability. Because if each one of these microservices comes with its own tech stack, when you're thinking about deployment, things could actually get quite complex if you're not really clever about it. When you're thinking about refactoring, it might be more difficult to refactor when everything is so small-grained in its decomposition. So recognize there are architectural trade-offs, and when you move to a microservice architecture, which might be an entirely good idea, you don't get an architecture free. And you really need to think about it. So if I look at an evolution of where business applications have come, we've gone from monoliths to 2-tier, 3-tier, SOA, cloud strategies, we've got microservices, and we have really made great strides in how we decompose and how we make things more modular and how we support change. But the persisting themes still are modularity. Modularity maybe in a more dynamic way, but modularity. And how actually we are able to reuse things and still support the kind of variation and agility we need in the marketplace to create continuous value. So let me just touch on scale briefly. I led a nice little study at the SEI, a study on ultra-large scale systems, systems of the future. This was in 2006. They were systems of the future in 2006. Right now, they're the systems that Grady Booch talks about, that these are really different systems. And they are really different systems because scale does change everything. It changes the way we think about decomposing. It changes the idea that we can beat all the bugs out of a system. It ain't happening, folks. It just isn't. You're going to have unprecedented conditions that you've never intended because things are going to be connected that you never imagined would be connected. And on, but that's a whole other talk and another time. So let me just focus momentarily on 3 of my favorites: cloud strategies for mobility and big data. Okay, cloud, everybody's drinking this water of virtualization. We go to clouds because of the elasticity, the scalability, and the economics. We're not storing all the data. But recognize there are 2 different business models, the business model of the cloud providers and the business model of the cloud consumers, and the quality attributes of primary interest to both are different. If you're a cloud provider, you're looking at saving energy because then you're saving money. You may be green, but I think green is a consequence of saving money. And you want to honor the SLA, okay? If you are the consumer, you're thinking about performance, you're thinking about privacy, you're thinking about security, and those things don't always fall out of the SLA, and you are not in control. So you better architect accordingly. Mobility. All of applications data being pushed to mobile devices, whether they're smartphones or tablets or phablets or whatever it is you're using. And with that, we have a tremendous appetite for communicating and viewing over our mobile platforms. Right now, there are more people who are in front of their mobile devices than who watch television. They spend more hours in front of their mobile devices than television. That's kind of interesting. There are more mobile devices than there are laptops and desktop machines. Now, here's the problem. We're expecting the same sort of behavior from those mobile devices that we get from the desktops and the laptops, but there are battery limitations. And the end-to-end latency between your mobile device and the cloud that's providing you the information can vary greatly depending on where you are. And I would say if you are in a more disadvantaged part of the world, you're going to suffer these consequences much more greatly than you would here. So what are people doing? What are the architectural strategies? The architectural strategies here are pushing things to the edge, pushing more applications, more data to the edge, and then using surrogates. Surrogates that would allow for a single hop from the mobile device to a fog, a cloudlet, some other sort of in-between place from the cloud to the mobile device where you can do computation offload and data transfer. So something that is very important, we are working in this area at the SEI, working on something called cloudlets, because one of the communities we serve is the defense community, and soldiers on the battlefield with their mobile devices are often disconnected, and there isn't continuous connectivity for them. Big data. Big data, mentioned tsunamis of data. Well, essentially, there are two distinct but related technological thrusts. You've got your data analytics and your infrastructure. Basically, the data analytics is taking huge amounts of heterogeneous data, passing them through a filter so that you can make decisions and have intelligent information. On the infrastructure side, wow, we've got to be fast, scalable, secure, easy to use, and folks, there are trade-offs all the way down this stack. So use your NewSQL and NoSQL databases, but they don't all come equal. They don't all support the same quality attributes. They don't all have the same services that you would need. And so when you're thinking about architecting your big data system, what you've got to be able to do is scale, increase capacity, but at a rate that's much greater than the cost goes up. And very often, when we increase capacity, when we scale, we introduce complexity, and the complexity costs. In a big data system, you have to architect it so that it is self-monitoring, because you will not be able to catch all of what you would want to catch by way of errors or operational defects that would be killers during testing. It's just not possible. So you're going to have to use logging, you're going to have to use metrics and monitoring, and oh, by the way, all of the new databases that we have do not come with governors. Now, assurance. I think by now, I've convinced you, or hopefully, or you're asleep, or you're taking pictures or something, I don't know. We'll bring Billy Price back soon. That the architecture is the mechanism for reasoning about the behavior of the system. And the behavior is how we want it to behave. We want to be able to assure that it will be secure, that it will be able to perform as it's intended. But there are a lot of things in the mix just now. You've got all kinds of supply chains and open source that you're using. You've got all kinds of tool chains that you're using. And the consequences appear in operational and security and in reputations to companies. I read an article today, actually the incident happened in February of this year, where a medical procedure was being performed with a medical device. The procedure was a heart catheterization, and the medical device was connected to a laptop for logging and monitoring. Well, the system crashed because the laptop's antivirus software did a scan. And when the antivirus software did a scan, the whole system went down. Having had a heart catheterization, I would not really have welcomed that sort of a software breakdown. So it is really important that we assure systems, and especially with the Internet of Things. Now, we've talked a lot about the Internet of Things, and it is a heady idea. The idea that Gartner says that in 2025, 25 billion things will be connected. Grady Booch said billions of billions. That's great. But how do you assure all that? And when I think about my self-driving car, I am all about a self-driving car. If anybody's driven with me, they totally get why I'm about a self-driving car. But then I think about my grandkids in the back of that car. Or you might think about your children. It's worse with grandkids because they're the kids of your kids. The responsibility is way high. But think about what you need to do. Michael Keeling gave a nice talk about ethics, and I really think it is a quality attribute, and I really think that we owe it to ourselves to think about how we are analyzing our architectures and whether or not we're doing that. It's not just a phase, it's ongoing. And there are lots of different ways to capture an architecture. I mean, you can do it on a wiki. Who was it in one of the talks said, you can't get people now to write a 10-page Word document, but people will write 200-page wikis. Go for it. If it's on a wiki, if it's in a Visio diagram, it needs to be analyzed. You need to visit it often. And if you have a safety critical system, more is required. Use a formal description language. In my humble opinion, we need more tooling and automation here. So let me bring it back to end. I think there's tension. And I think these are the big challenges of our time. And we really need to rise to the challenge and think about the architecture decisions we make. And we need to make these architecture decisions in an educated way. I have a son who's in the software biz, and he writes a blog. You can check him out, Ben Northrop. It's Northrop with an OP. And he wrote a blog, Let's Not Be Slaves to Fashion. Because he was sick of going to big developer conferences where people said, are you using Go? Well, you can't be doing Agile if you're not using this technique. And it's all about the fad. And we've got to be careful. A lot of these technologies are seductive. A lot of the new tools, a lot of the new techniques are really appealing. But we've got to be mindful of the choices we make and make sure they're appropriate for the architectures we're building. George Fairbanks gave a wonderful talk at this SATURN, and he talked about this very thing, about pausing and reflecting on your architecture. So there's this whole movement in the world right now, and it's born out of the yoga culture, and it's called mindfulness. Are you all down with mindfulness? Because we're so busy in our lives, we need to sit for 15 minutes and be silent and be mindful, because we need to be in the moment. If you're here at SATURN, you're listening to me. If your child is talking to you, you're not texting your colleagues, you're not on a conference call, you're talking to your child. Well, I've decided that what we need is mindful architecting. We really need to have some mindful sessions about our architecture. Take time out, because I think that's the only way that we're going to get a handle on technical debt and adhere to release cycles and have any sort of assurance and be responsible in this brave new world of the systems that are possible. So let me end my little journey, my little reflection. From my perspective, from my window on the software development world, I think we've got strong foundations. I think a lot of progress has been made. There are a lot of changes, and those changes really emanate from the connectivity in the world, from the internet and the wireless networks that we have. And they have spawned new technologies and approaches and challenges. But to me, the software architecture principles and the importance of software architecture persists. But I think there's a lot to be done. A colleague of mine at Carnegie Mellon, Bill Shirless, says that software is the building material of our world. That makes your responsible heady. The future is yours. Be mindful about it. Thanks. And I want to thank all those people at the SAI whose thoughts have influenced me over the years. Thank you for being here. Thanks for carrying on the tradition of SATURN.